Satellites. How do they know where they are and where to go next? The process that answers these questions is called attitude estimation. It is a never ending loop of the satellite asking itself, where am I and where am I looking? Where am I and where am I looking? To answer these questions, satellites use magnetic field sensors, which are meant to read Earth's magnetic field and output a value. However, like any sensor in real life, these magnetic field sensors are noisy. Not only are the sensors noisy, but the devices used to rotate satellites, called magnetorquers, produce a magnetic field that also affects the reading of these sensors. Magnetic field sensors read the magnetic field in all three directions on the satellite, X, Y, and Z. This data is simulated readings of the magnetic field in orange and the simulated true magnetic field in blue. The goal is to get the orange line as close to the blue as possible after we run it through a filter. Introducing the Kalman filter. This is a math tool used by engineers to make sensor readings more accurate. The way the Kalman filter works is by using this equation. Estimate equals prediction plus correction. Here is the math behind it. Warning, there is lots of ugly math here, but the good news is that it is not very important you, the viewer, understand all this math. You just need to understand what matrices Q and R do, which I'll get to in a minute. The Kalman filter uses two steps. The first step is the prediction step. You estimate the state based on previous information. At each time step k, you calculate the predicted state x hat at time step k given the k minus 1 step, and the predicted uncertainty p at time k given the k minus 1 step. Additionally, you add the process noise covariance matrix q, which is a constant. The second step is the update step, which refines the estimate using the new measurement, zk. In this step, you first calculate the Kalman gain matrix, big K, at time k, which comes from the predicted uncertainty from step 1, and the measurement noise covariance matrix, R, which is a constant. Then you calculate the final updated estimate and updated uncertainty using big K. I will set Q and R to be square identity matrices with coefficients alpha and beta, respectively. Alpha and beta will each iterate through the values 0.01, 0.1, 1, 10, and 100. As we plug in each of these values, we will evaluate the cost function. In this case, the cost function is the difference between the true magnetic field, which is known by the simulation, and the estimated magnetic field by the Kalman filter. This difference is squared and calculated at every time step. All these values at all time steps are added together to get the total error, giving a specific Q and R. As we iterate through the different Q and R matrices, we store whichever one gives us the lowest error. This is called grid search, which is simple as you saw, but not the best we can do, since the optimal value of alpha could be 0.2 or 7.5 or something like that. Not necessarily 0.1, 1, or 10 exactly. This plot shows the best estimate the Kalman filter could do after grid search, which isn't great. In order to make the optimization better, it would be nice to iterate through plenty of values of alpha and beta. Or better yet, run all of this through an optimization algorithm that gives us the optimal alpha and beta. To do this, I implemented SciPy's minimize function using Nelder-Mead's method. This is the plot now, which definitely shows a better Kalman filter estimate. I also printed the value of the cost function from earlier, and this is what I came up with. Pretty neat. I tried plenty of other methods and found that the best method is Powell's. This is the plot of the Kalman filter estimate and the cost function value. It's hard to tell if it's better than the Nelder-Mead's graph, but the math doesn't lie, and the math says the cost function for this one is lower. Well, that was a lot of math and graphs, so let me summarize everything by talking to the camera to hopefully make it seem more human. There is a cost function that we want to minimize, and there are hyperparameters Q and R, which are the identity matrix but multiplied by factors alpha and beta, respectively. I ran an optimization algorithm to find the best values for alpha and beta using Powell's algorithm, and I landed on the following values. For alpha, I got 0.0000136, and for beta, I got 0.00619. And that was everything. Thank you for watching.